Hey guys, welcome back to Recreational Sniper. Tonight we're going to look at building some drop charts for the 6.5 Creedmoor you see behind me. It is a Uintall precision bolt action upper for an AR-10 lower. I do have an AR-10 upper in 6.5 Creedmoor with a 16-inch barrel setup. This Uintall precision bolt action upper has a 26-inch barrel setup. So we're going to build drop charts for it, and I've already kind of started on this project, so I'm going to go ahead and open that. And you can see on the 28 inches of mercury chart, I do not have my gyroscopic stability fixed for that, so we're going to have to fix the gyroscopic stability factor for that chart in particular. Now these are 100 yard increment charts, and I'm using yard increments with this particular rifle because it is set up in minutes of angle, and minutes of angle tend to be a little bit easier to use with yards when it comes to the math versus using minutes of angle with meters, and vice versa. If we were using mils, it would be easier to use mils with meters. So that's the reason why my 308 charts are set up in meters and my scope on my 308 is set up in mils. It does sound like it can be pretty confusing to switch between the two different ones, but I've done both of those different units of measurement long enough that I'm pretty good at being able to know and differentiate between the two and keep everything separate. So that's also the reason why we're looking at these charts, because I can immediately look at the turret caps on my minute of angle scope and say, hey, that's clearly in minutes of angle. It says it right on top, so we want to be looking at minute of angle charts automatically. And same thing when it comes to my mil turrets on my mil-radian scopes. So with that being said, we're going to fix this gyroscopic stability here because this is not correct for 28 inches of mercury. So we're going to go ahead and fix that. We're going to have to open up the internet, and what we're going to do is we're going to go to the Burger stability calculator here. And the bullet we're using, as far as JVM Ballistics is concerned, they are, because this is already set up, if we look at it, it's already in G1 perspective, so they're using the G1 drag function. So we're going to go ahead and use that for our twist rate stability calculator. So we're going to leave this in G1, and we're going to type in 636 for our G1, and this is a 264 caliber. If you don't know, 6.5 millimeter and 264 are the same diameter, so 0.264 inches or 6.5 millimeters are exactly the same. And we are running a 144 grain FMJ, and the overall length is 1.295 inches, and the muzzle velocity for our standard units of measurement is going to be 2897, and we're running a 1 1/8 inch twist, and we are also at our standard units, we are at 70 degrees Fahrenheit, but for 28 inches of mercury, the average altitude for 28 inches of mercury is going to be 1,874 feet. Give or take, it's going to change, and that can vary by 20 or 30 feet either direction. But on average, around the world, if you are measuring 28 inches of mercury, you're going to be on average at 1,874 feet. So that's how we're going to calculate this. And we're going to get 2.30 as our gyroscopic stability factor here. So we're going to go back over to our chart, and we're going to fix this and say let's double check here. 70 degrees, 1874, at 28 inches. Yes, okay. We're correct at 2.3. So 2.30 is our gyroscopic stability factor. We will have to know what that is to be able to actually mathematically figure out what our spin drift is. Okay. Alright, now we need one more chart, and we need one more for 27 inches of mercury. I could go ahead and build these for like 26 inches of mercury, 25, 24, etc. And, you know, build them to where, you know, I could have drop charts that would be effective in any altitude range, you know, up to, say, 10,000 feet in altitude. But the reality is, I really hope that I don't end up in a situation where I have to be making extremely precise, extreme range shots at 10,000 feet in altitude. So I'm not really going to worry with building those charts right now. So what we're going to do is we're going to go back into JVM Ballistics over here, and we're going to go back and we're going to take this to 27 inches of mercury, which is roughly, on average, anywhere in the world, on average, not saying it's exact, is going to be about 2,902 feet in altitude on average. And we're going to go ahead and leave that at 70 degrees. And we're going to leave our muzzle velocity at 2897. And we're going to go ahead and calculate that. So, here we go. Before we get too carried away, what we're going to do over here is we need a template. So we're going to go ahead and we're going to, kind of screwed up there, got a little ahead of myself. We're going to select this, and we're going to copy it, come down, and we're going to paste it exactly the way it is. And then we're going to change a few things. Immediately we're going to go in here and we're going to change our barometric pressure to 27 inches for this chart. And we're going to change this one to 27, just kind of a little bit redundant. And then we can go ahead and kind of just clear this whole thing out right here. So we'll clear the contents, and then we'll start from scratch. Okay? The only thing we're leaving is our muzzle velocity, because we know at 70 degrees Fahrenheit we get this muzzle velocity as long as the ammunition is at 70 degrees and the ambient air temperature is at 70 degrees. That's our average velocity. And same thing for 80 degrees. As long as it's 80 degrees ammunition and ambient air temperature, we get 2,914 feet per second. So we're going to leave that alone. And we're going to leave this stuff alone because those are our standard units. Okay, so let's go back over here and we're going to copy this down. Now, again, with this particular setup, we have a scope that is 108 minutes of angle of full range of adjustment, which means we really only have 54 minutes of usable adjustment range in the scope. Okay, now the scope is mounted onto a 20-minute of angle rail on top of the rifle, so it's mounted onto 20 minutes of angle, so we can add 20 minutes of angle to 54 minutes of angle, and that will tell us that we have a maximum usable adjustment range of 74 minutes of angle on this particular rifle. So what we're going to do is we're going to look at this thing, and we're going to go all the way down here, and you see at 1,800 yards we're showing 69.3 minutes of angle of drop, and at 1,900 yards it jumps to 77.2 minutes of angle. So we're technically, we could shoot somewhere in between there, probably around 1,840 yards before we max out our adjustment, but this is a 100-yard increment chart, so our maximum range is going to be 1,800 yards for this temperature and muzzle velocity, so, and altitude. So yeah, tons of stuff to keep track of there. Hang on, what happened here? We're gonna copy this, and we're gonna go over here, and we're gonna paste it up. So we're all good there. We're gonna go ahead and take this. We're gonna copy it and drop it right here, and then we're gonna do the same thing for wind. Copy that, drop it in the wind column, and then we're gonna get over here and copy our target lead, and then our time of flight. Copy. So we're only doing this for the 70-degree column, where we're copying everything over there, our wind drift and our target lead and our time of flight. For the other temperature range columns, we're not going to really worry about that too much. In extreme cases, it would become important to know those things, but for practical purposes, which is what these charts are for, practical use, expedient use, we're not really going to worry about having to print out tons and tons of information, because if we did it for every variable and every temperature range and stuff, these charts would be huge and very hard to navigate and very confusing, and we kind of want to avoid having that problem. We want to be able to navigate the charts easily, pick out a firing solution in a very quick and easy manner, and be able to effectively engage targets at whatever range that we are shooting at. So we're looking at this deal here. We can come down here, and it actually, our supersonic range extends at this altitude out to 1900 yards, so it's not even on the map, but we can't actually adjust to 1900 yards in our scope, so we're just not going to worry about it. We're just going to go ahead and clear these out and leave those as no fill. Now we are going to say that, hey, we've got at least 500 foot-pounds muzzle energy to 1500 yards, so we're going to leave that highlighted there in red. And then we're going to look up here at 1,000 foot-pounds of energy. We've got it to 900 yards, so we're going to leave that highlighted in orange. That's important. I'll go ahead and highlight these to make them match the rest of them there. That's fine. So we really didn't have to do much here as far as any crazy adjustments. So let's go back to JBM Ballistics, and let's change it up to 80 degrees Fahrenheit. Okay. So at 80 degrees Fahrenheit, we would have 2,914 feet per second based on our observations, based on what we've recorded in the field at 80 degrees, and leave everything else the same. Go ahead and calculate it. Now look at us. We still don't have enough elevation range to get us to 1900 yards. That bullet is really falling on its nose out there at that range, but 1800 is still doable, and our supersonic range is actually still at 1900 yards, so well past a mile. And what we'll do is we'll just paste it right over the top of these, and then we'll take our elevation and we'll copy it, paste it in there, and you'll notice that at our little bit higher velocity, at a little higher temperature, which means the atmosphere is a little less dense, a little thinner air, our bullet is going to fly a little bit higher, a little bit flatter, a little bit faster for a little bit longer, and we have just a little bit less drop, about 2 minutes of angle less drop. Now 2 minutes of angle at that distance is about 36 inches. That's about 3 feet less drop at 1800 yards. So they kind of let you know that if you're going to shoot extreme range, you kind of need to know these things, because 3 feet is a pretty big, that's a pretty big discrepancy there. If you don't know that your bullet's flying that much higher and that much faster and flatter and whatnot. Okay? So we are going to go back and we're going to look at our 500 foot-pound mark and look at 80 degrees, and at that muzzle velocity at 2914, our 500 foot-pound threshold moves up to 1600. So we're going to go over to 1600. We are going to mark it red, and we're going to change this one to normal. And then our 1000 foot-pound mark is still at 900. We didn't quite break 1,000 foot-pounds at the 1,000 yard area, so we're going to leave it alone at 900. And now we need to fix our gyroscopic stability factor, so we're going to go back over here to the burger twist rate deal, and we're going to leave our velocity alone, we're going to leave our temperature alone. The only thing we're going to change is our elevation to 2902. And we're going to get a 2.39 stability factor. So we want to save that onto here. So there we go. We've got charts built so far for at least the 70 and 80 degree temperature zones. We have not done any testing in 0, 30, 50, or 60, or 90 or 100 degrees yet. At least we have not done that with ammunition at that temperature. But we've got plenty of data at 70 degrees and plenty of data at 80 degrees to know that these are the average velocities that we are recording with our particular rifle and the particular ammunition. So you're going to want to build one of these charts for each kind of ammunition that you are shooting and each rifle that you are shooting specifically, because not all rifles are equal. For instance, 2,900 feet per second with a 144 grain 6.5 Creedmoor round is very, very high velocity, but it is still very accurate, and we're talking 1 minute of angle or less accuracy, and it also is not showing any signs of pressure. So I'm thinking that has something to do with this Power Pro 4000 MR powder combined with a Magnum large rifle primer in the Hornady brass with the 144 grain Lapua FMJ. I don't know, maybe that bullet's just a little bit slipperier than others, but we're getting fantastic velocities out of it with no signs of pressure, which means we get fantastic range out of it. This thing actually surpasses my 6.5 PRC for now. I have not actually done any hand loading for the PRC other than a few test rounds, but I have not been able to see any sort of velocity like I am actually getting out of the Creedmoor. So, you know, weird things happen with different guns. This Creedmoor is an absolute hammer, though. This very, you know, particular rifle that I've got here. So, in the next video, we are going to break this down again. Only instead of 100 yard increments, we're going to do it in 10 yard increments, and we will have those printed out as well. So the cool thing about the 100 yard increments is you can kind of scale this down a little bit and then laminate it, and then you can you know, if you got a normal rifle stock, you can stick it to the rifle stock, just kind of tape it on there if you want. A lot of these skeletonized you know, match rifles, target rifles and stuff don't really have a nice surface area to stick a card on, but you can laminate this thing, and it's very packable, waterproof, and that sort of thing. It's just something to keep with you at all times, you know, out in the field. The much larger versions that we're going to do in 10 yard increments that are going to be used for like really, really precise shots, those, you know, you could laminate them, but you're going to have several sheets of laminated paper and stuff. And then if you're, you know, carrying multiple charts for multiple rifles and that sort of thing, it can get kind of cumbersome, but that's just how it goes. So I hope you guys enjoyed watching this, and we will see you later in the next video. Thanks for watching.